Welcome friends to my YouTube channel. Now in my last lecture I told about the triple point. Okay, I discussed about the thermodynamics of triple point. Now in this lecture I shall going to discuss an important topic related to phase transition, that is phase rule. Okay, that is I am going to discuss Gibbs phase rule. Okay, now before starting the phase rule you must have to know two terms. First one is what is phase, and the second one is what is component. You have to know these two terms. Okay, so first of all I come to the first term, that is phase. Now as I told earlier that a phase is nothing but a form of matter that is physically or chemically uniform. Okay, so it is nothing but a form of matter that is physically and chemically uniform. Physically or chemically uniform, or you can say more commonly that a homogeneous part of a heterogeneous system that is separated from all other parts by distinguishable boundary. Okay, so homogeneous, or you can say the homogeneous part of a heterogeneous system, that is separated from all other parts by distinguishable boundary, is called phase, that I told earlier. Okay, now let us take two examples so it will be clear. Okay, so if we took few examples it will be more clear to you. Now suppose first example you can take that ice water vapor. Clearly it is a three phase system, ice, water and vapor. So it is a three phase system. It is a common example. So ice, water, vapor constitutes a three phase system. So it is a three phase system. Okay. Now let us take another example. Say two immiscible liquids. Okay. Say two immiscible liquids. Just take an example, say benzene water. Okay, benzene water. These two immiscible liquids, take the example of benzene water. So it is a two phase, because the two liquids are immiscible. You can easily distinguish them, benzene and water. There is a two phase. Now two miscible liquids, say if you take two miscible liquids, say alcohol, water, so it constitutes single phase. Okay, it constitutes a single phase. Okay, so when you are talking about two immiscible liquids, you can easily distinguish the two layers of liquids, so that constitute two phase. And if you talk about two miscible liquids, say water and alcohol, they mix up, so as a result it constitute one phase. Okay, so this is what about phase with example. Now let us move to the second term, that is component. What is component? The minimum number of independent variables required to represent the composition of each phase. Okay, so minimum number of independent variables require, minimum number of independent variables require, minimum number of independent variables require to represent the composition of each phase, composition of each phase is called component, is called the component. Okay, so component is nothing but the minimum number of independent variables or coordinates required to represent the composition of each phase. Okay, now just see this. Suppose this is P1 phase, this is P2 phase, this is P3 phase, and there are C components in different phases. Says this is C1, C2, C3. Here also C1, C2, C3. Here also C1, C2, C3. Okay, so you can see that the composition of each and every phase can be represented by these C1, C2, C3, C1. So these are components. Okay, you can see from the picture that each and every phase constitutes components C1, C2, C3. So each phase can be expressed in terms of different components. So that is the definition, the minimum number of independent variables required to represent the composition of each phase. Okay, now let us take suitable example so it will be clear to you. Okay, now suppose take the common example, ice water vapor, ice water vapor. Okay, what is the sign of ice? You write ice as H2O, you write water as also H2O, and you write this H2O. Just this is S, this is L, and this is V. But the chemical composition of each phases can be represented by H2O. So it is a one component system. Why ice water vapor is a one component system? There are three different phases obviously, but the chemical composition is expressed by H2O of all the three phases. So it is only a one component system. Let us take another example, say sulfur. Okay, if you take the example of sulfur, then there are four phases of sulfur: rhombic, monoclinic, liquid, and vapor. Okay, rhombic, monoclinic, liquid, and vapor. There are four phases of sulfur: rhombic, monoclinic, liquid, and vapor. But chemical composition of every phase can be represented by this. So it is also a one component system. Okay, since the chemical composition is one and unique, it is a one component system. Okay, so this is what about phase and component. Okay, now an important thing is that now the next thing is that Gibbs phase rule. Okay, Gibbs phase rule. What is Gibbs phase rule? Okay, now what is phase rule? Now if the equilibrium condition between two phases, if the equilibrium condition between the two phases are not affected by electric, magnetic, or gravity forces but affected by pressure, temperature, and concentration. Okay, concentration. Okay, the equilibrium condition is not say influenced by gravity forces or magnetic or electric forces, but influenced by this, say, pressure, temperature, concentration. Then the total number of degrees of freedom F is related to P number of phases and C number of components by this relation, F equals to C minus P plus 2. So this is Gibbs phase rule. So equilibrium condition is only disturbed by pressure, temperature, and concentration. So the degrees of freedom F is related to P number of phases and C number of components by this relation. Okay. So this is Gibbs phase rule. Okay. So let us see how it agrees. Okay. Now, in order to prove the Gibbs phase rule, we first assume that internal energy is a homogeneous function of entropy, volume, and different masses of the substances. Okay, different masses of substances. We assume this, that internal energy is a homogeneous function of entropy, volume, and the masses of different substances, say m1 m2 mc for c number of concentrations. So what will be my du? My du will be del u del s ds, say del u del v dv, plus you can write del u, that is del m1 dm1, and you can write this del u del mc dmc. Now these masses are constants. Okay, m1 m2 m3 mc etc are constants. So dm1 dot 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 dmc, all terms cancel since the masses are constants. Okay, now since the masses are constants, these terms vanishes. So what you can write, only remain the first two terms, del u del s ds plus say del u del v dv. Okay, now from combined form of first and second law, du you can write as t ds minus p dv. So comparing, what we can write, del u del s, this we can write as t. Comparing, we can write del u del s t, and del u del v, this we can write minus p. Okay, since the masses are constant, these terms cancels, only remains these two terms, and from combined form of first and second law we can write this. So combine these two, we can write del u del s t and del u del v equal to minus p. Now if we substitute these values in the original equation, that is del u del s will be t. Okay, so what we get? Now if we substitute these values in this equation, we ultimately get du, this equals to t ds minus p dv. Say this I can say mu1 dm1 plus mu2 dm2 plus dot 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 mu c dmc. Okay, mu1 means del u del m1, increase in internal energy per unit mass in case of first particle. Mu2 del u del m2, increase in internal energy per unit mass for the second particle. Okay, so in this way. Now what is the formula of Gibbs potential? Gibbs potential can be written as u plus pv minus ts. Okay, now what will be my dg? My dg will be du. So substitute that value of du, tds minus pdv plus mu1 dm1 plus mu2 dm2 plus dot 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 mu c dmc, and this is obviously p, when you do it, pdv plus vdp, this is say minus tds, and this is say minus sdt. So tds cancels, minus pdv plus pdv cancels, only remain dp term, dt term, and dg term. These are okay. Now you all know that Gibbs potential energy dg tends to 0 at constant pressure and temperature. That you all know, that at constant pressure and temperature dg tends to 0. So if you put dg equal to 0, then you make these two terms 0, that is dp and dt 0. So from which we can easily conclude, okay, from which we can easily write mu1 dm1 plus mu2 dm2 mu c dmc, this equals to 0. Okay, mu c dmc, this is equal to 0. mu1 dm1 plus mu2 dm2 plus mu c dmc. Okay, so they give it a name, say 1. Now again we told about that internal energy is a homogeneous function of S, V and the different masses that we assume. Now what we write by using Euler theorem? If U is a function of these quantities of degree 1, then what will be the formula? N into U. This is equals to x into del f del x. That means del U del S plus V into del U del V plus M1 into del U del M1 plus M2 into del U del M2 plus MC into del U del MC. Okay. Now since it is a U is a function of these quantities of degree 1, you can put n equal to 1 since the degree is 1. So you can write U, this equals to, what is this? This is T, TS and this is P, PV plus you can write this is mu1. So mu1 M1 plus mu2 M2 plus mu C MC. Okay, this you can also write. Now this is G. Okay, so this is G, U plus PV minus TS, this we can write G. So from which we can write G, this equals to mu1 M1 plus mu2 M2 plus mu C MC. So what will be my DG? My DG will be mu1 dm1 plus m1 d mu1 plus mu2 dm2 plus m2 d mu2 plus mu c dmc plus mc d mu c. Now at equilibrium condition, what happens? You apply this. So this term and this term becomes 0, and in equilibrium dg tends to 0 at constant pressure and temperature. So you can clearly write this equation, m1 d mu1 plus m2 d mu2 plus mc say d mu c, this is 0. The marker is almost finished, so I have to buy a new one, so forgive me if there is any mistake. Okay, so we can write up to this equation. Okay, so it's fine. So the chemical potential, we define the increase in internal energy per unit mass, or you can say the condition of equilibrium. Now one thing, say here in order to find out the degree of freedom, at first we have to find out the total number of variables. And what are the total number of variables? Pressure and temperature. So total number of variables will be what? At first, pressure and temperature. So there are two variables. Okay, now in each phase there are C different components. Okay, C different components. So if you choose the concentration of C minus 1 component, then the remaining last one will be fixed. Why? Just take an example. Say x plus y plus z equal to 1. This represents the state of a system. So in order to represent the state of a system, there are 3 variables, but you need not to require the value of 3 variables to represent the state of a system. You can require only 2 variables, because once you know the value of 2 variables, you can easily find the third one. So there are 3 variables, but you require 3 minus 1. That means 2 variables are sufficient to represent